Hello, everybody. I hope you all had a good Tuesday so far, and good morning or good evening or wherever you are. So my name is Christine. I'm happy to welcome you here to this cruise webinar presented today by Marilaure Grégoire, who is Director of Research and Professor of Marine Ecosystem Modeling at the Liège University in Belgium. She has graduated in physical engineering and has a PhD in applied science on the development of three-dimensional numerical models. She worked in several European projects and is also involved in the European Copernicus Marine Environment Service. Right now, she also acted as the editor of the Journal of Biogeoscience, and I'm also very happy about that. She's co-chairing the IOC working group, Global Ocean Oxygen Network. And I'm looking very much forward to her presentation on deoxygenation in the global and coastal ocean, challenges of observing and modeling low oxygen zones, GO2NE, the Global Ocean Oxygen Network. She will present here for around 30 minutes. Sorry, and you all will have the possibility to type your questions, and there will be roughly a 30-minute session afterwards where you will answer your questions, and I hope we will have a good interaction afterwards. So I'm turning my webcam off now, and I'm looking forward to the next 30 minutes. The floor is yours, Marilaure.
Okay, so thank you, Kirsten, for this introduction, and good afternoon, everyone. Thank you for being here to hear this talk about oxygen and deoxygenation. So the title of the talk is Deoxygenation in the Global and Coastal Ocean, Challenges of Observing and Modeling these Low Oxygen Zones. And this talk is made by myself and also the GO2NE group. So GO2NE, it's the Global Ocean Oxygen Network. So it's a working group, a research network that has been initiated about 2 years ago with the support of IOC-Unesco. And this group involved more or less 20 people. You can see the picture of the group here. So this picture has been taken in September last week during our annual meeting. And so you can see that we are more or less 20 people with different expertise, but working all in oxygen and deoxygenation in the global and coastal ocean. So I will come back at the end of the talk about the main outputs of the group as concerned deoxygenation, but first I will present my talk. I will give my talk. So first, a reminder, so where do we have low oxygen regions? So low oxygen region can be found in the coastal, open ocean, and also in semi-enclosed sea. As low oxygen region, we speak about water which have a level of oxygen that is below 2 milligrams per liter. So this threshold is usually used, but of course this threshold can be discussed afterwards. So if we look at the mapping, so we can see that for the coastal area, we have more or less 500 sites or several hundred sites. And in the deep ocean, we have the sites that are shown here in blue. And this amounts to several million cubic kilometers of waters which have low oxygen concentration. So what happened with the oxygen in the global and the coastal ocean? So for the open ocean, there are several papers that show that since 1960, the global ocean oxygen content is decreasing by more or less 1 to 2%. So this is a decrease of the global oxygen inventory, which represents more or less 70 billion tons since 1960. So this decrease is not uniform, as you can see here on the map that show the decrease of oxygen or vertically integrated oxygen per decade. And you can see that you have hotspots of changes which are mainly located in the North and in the tropical Pacific, in the Southern and Arctic Ocean, and also in the South Atlantic region. Over the vertical, there are also regions that are more affected by the phenomenon of deoxygenation. This is region located in the region of the main thermocline, mainly between 100 and 300 meters. So if we speak about the oxygen budget of the ocean, of course, we also have to consider the oxygen budget of the atmosphere, because we know that since the beginning, the ocean and the atmosphere are strongly coupled. And so these pictures show you global oxygen budget for the ocean and the atmosphere. This is expressed in petamole of oxygen per year, and the content in red are expressed in petamole of oxygen. So what you can see is that the oxygen inventory of the ocean only represents 0.6% of the oxygen inventory of the atmosphere. And this makes that the oxygen content of the ocean is very sensitive to changes, in its dynamics. So if we look at the process that affect the oxygen inventory of the atmosphere, we see that the oxygen will decrease due, of course, to the fossil fuel burning mainly, but also due to volcanism and weathering process. And for the source of oxygen, we have a net land source that comes from the biosphere. For the ocean, roughly, we have an equilibrium between the amount of oxygen produced by photosynthesis and the amount of oxygen consumed by respiration over the whole ocean, except for a small barrier rate that will consist in a source of oxygen for the atmosphere afterwards. But more or less, this is well balanced. But what's happened is that the photosynthesis mainly occurs in the surface, and so we produce oxygen in the surface, but respiration occurs at depths, so below 100 meters. And so this makes that in some region where you do not have ventilation mechanism to resupply oxygen from the surface to the subsurface, you can have a decrease of the, you can have an equilibrium that goes to very low oxygen concentration, and this low oxygen concentration can be below some threshold that we use to define an oxygen minimum zone. And so the recent evidence show that these oxygen minimum zones are expanding since the last decades. So why is deoxygenation ongoing in the global ocean? So this is a very tricky question, very difficult question. So several investigations using models and observation analysis have shown that warming-induced solubility change can only explain 15% of the decrease of oxygen. So what about the remaining 85%? So this remaining 85% can be due to a slowdown of the meridional overturning circulation, which can be due to change in the winds in the Antarctic and in the Arctic Ocean, can be also due to reduced ventilation in the deep convection region, can also be due to reduced mixed layer subduction due to increased stratification associated to global warming, but can also be due to natural climate variability, as shown by several papers, and among them we have one that is recently published in Biogeoscience Discussion by Dutheil et al. That showed that this natural variability can play an important role in explaining the decrease of oxygen. So here, models are very important to explain, to gain a mechanistic understanding of the relative importance of these processes. For the coastal ocean, we also have evidence of a decrease of the oxygen content of the bottom layer. And so this graph shows you the evolution of the number of systems with hypoxia, so with low oxygen concentration, since 1950. And you can see that the number of sites where you have hypoxic condition is rapidly rising. And this, if you look at the map, you can see that you have these sites in all the continents, and the extension is usually several 10,000 of square kilometers, you can see here. And this is due to the fact that since 1950, we are able to synthesize synthetically, we are able to synthesize fixed nitrogen, reactive nitrogen, which is nitrate and ammonium. And so due to the fact that we are able to produce industrially this reactive nitrogen, we have an explosion of the use of fertilizer in agriculture, which increased considerably the amount of nitrate and ammonium brought to the coastal zone. This leads to eutrophication. As you can see here, you have a picture that shows the situation of the coastal ocean. And so in the coastal ocean, where you have inputs of inorganic nutrients, this input of inorganic nutrients will lead to important blooms that you can see here in green. This bloom will be degraded and sink to the bottom. And when it sinks to the bottom, if you have stratification, this stratification will prevent the replenishment of bottom water in oxygen. And so since you have huge amount of organic material on the bottom, this degradation of the organic matter on the bottom will consume high amount of oxygen and will then generate a low oxygen zone on the bottom. So on the coastal area, this low oxygen zone can be periodic, can be persistent, can be occasional. You have several variability in this low oxygen region. They are caused by the humans. They happen in the bottom layer, and there the sediment processes are very important. If you want to understand what happened, the sediment is very important. In some extreme case, you can also have the outflow of hydrogen sulfide, and this substance is extremely toxic for living organisms, and this can be lethal for the organism that cannot escape to the outflow of this hydrogen sulfide. In a warming world, we expect that this problem of coastal hypoxia can intensify for several reasons. Because you will have change in the physics, because if you have an intensification of the pycnocline, you will have a reduction of the ventilation, but also because you will have an intensification of biological processes that can increase the consumption of oxygen. Now, if we speak about the biogeochemistry, so this figure shows you the global ocean nitrogen budget. So the flow is represented in teragram of nitrogen per year. So here in blue you have the natural nitrogen budget, and in red you have the impact of humans on this natural nitrogen budget. And what you can see is that the reactive nitrogen only represents 2% of the total nitrogen. So what is the reactive nitrogen? The reactive nitrogen is mainly nitrate and ammonium. So this is the nitrogen that can be used by most of the algae for performing photosynthesis. So this is really the nitrogen that will allow the development of photosynthesis. So this inventory is quite small, and the inventory of reactive nitrogen is mainly governed by nitrogen fixation that will increase the amount of reactive nitrogen. We also have atmospheric deposition and river discharge. And as a sink of reactive nitrogen, we have mainly denitrification. So denitrification that happened on the sediment for more or less 1/3 to a half of the total denitrification, and another part happened in the water column. If we go in a deoxygenation mode, then the extension of the oxygen minimum zone can intensify the amount of denitrification. And so this will increase the loss of reactive nitrogen for the system. This will have some impact on the primary production that we do not know, and this can also have impact on the rate fill nitrogen to phosphorus ratio of the water that we still don't know as well. So the big question now is to estimate if the nitrogen fixation would be able to compensate the potential increase of denitrification due to deoxygenation. Is it possible to have a balance? We don't know. What we know is that the nitrogen fixation requires high amounts of iron and phosphates. But what we know as well is that in a region that is affected by deoxygenation, the sediment will release iron and phosphate, and this iron and phosphate can stimulate the nitrogen fixation. And so this marine phosphorus cycle would be crucial to stabilize the marine nitrogen cycle by making the nitrogen fixation able to compensate for denitrification. But so far, we don't know if it will happen or not. If we speak about observation now, oxygen now is a key standard oceanographic variables. So here you have the ship observation that we have collected since 1950. This shows mainly the transect of the world ocean experiment and the Go ship experiment that you can see here since 1919. And this is on the left. On the right, you can see the biogeochemical Argo floats that are equipped with oxygen sensors. We have more and more floats. We have more or less 300 floats in the ocean now. And if you want to compare the number of profile that we have per year, deep sea profile that we have per year from Argo float and from ship profile, we can see that we have a ratio of more or less six more Argo floats compared to the ship profile now. So Argo float has really the potential to increase our knowledge of the oxygen cycling and the deoxygenation. But it has been shown that the oxygen sensor can drift. There are several papers on that. And this drift can be problematic in order to assess the long-term oxygen change. It's problematic because if you look at this map that has been taken from Stramma et al. 2012, you can see that the amount of oxygen trends is very small. So for instance, at 300 meters, the decrease per year of the oxygen concentration amounts to 0.6 macromole per kilogram. And so this is quite small, and so this put a lot of pressure on the accuracy that we need to have with the Argo float observation. So there are several corrections that have been proposed in order to correct for this drift and in order to make calibration. And we have a working group that have worked on that. This is the SCORE working group 142, which has been focused on the quality control procedure of oxygen sensor. And this group proposed a nice review paper that has been just published in Frontiers in Marine Science that made a lot of recommendations for the deployment and calibration of the Argo floats. So what can be retained, what are the main message, is that it is highly recommended to make an in-air calibration of the floats in order to achieve an accuracy of more or less 1 micromole per kilo over the lifetime of the float. So this is really needed to make this air calibration. And the figure on the right show you that if you make this air calibration, you are able, this is the blue curve, you are able to reproduce quite well the oxygen signal obtained from reference observation. So this will require that the optodes has to be mounted on the top of the cap floats in order to make an air measurement at the deployment, but also during the lifetime of the floats. So the question now is to know how the float that have been deployed before 2015 more or less can be corrected or not. That seems to be very challenging. And the other question is, okay, if we need to make this correction, there will be a difference between the near real-time product and the delay time product of oxygen. And this has to be taken into account for operational purposes when you have to assimilate oxygen in models. So if oxygen zones, low oxygen regions are very challenging to measure. So if you have very low oxygen concentration, we have seen, and this is the figure that is shown on your right, we have seen that the classic sensor, optical sensor, for instance, and other sensor will overestimate the oxygen concentration at very low concentration. So you have a comparison here of the seabird oxygen concentration estimation with the stock's oxygen concentration, and you can see that there is a difference. This difference is not important, but if you are targeting the estimation of anoxic marine zone and very low oxygen concentration, this could be important. And so thanks to this new measurement with Stock's sensor, it appears that a lot of regions in the Eastern Pacific were in fact anoxic marine zone and not oxygen minimum zone. So you do not have oxygen anymore. And another important conclusion that has been derived from this very accurate observation is that denitrification cannot occur if you have oxygen concentration higher than 1 micromole. So you really need to have almost no oxygen. Just nanomolar concentration can inhibit the denitrification process. And this new measurement can ask for a revision of the global nitrogen budget, and especially of the denitrification, because it seems that this denitrification can only occur if you do not have oxygen. So the volume of oxygen marine zone is still uncertain. So this is very difficult to estimate for the reason that I have just given to you. It is because you need very high accuracy concentration estimation. And so this paper by Bianchi et al. In 2016 show the bias that you can have from the world ocean climatology. So this is the gridded this is the World Ocean Climatology 2005, this is in the abscissa, and the reference observation that have been collected in oxygen minimum zone. And in some regions, this difference can be as high as 6.4 millimole of oxygen per cubic meter. Here, the difference is not only due between the difference between this climatology and the observation is not only due to the quality of the data, it can also be due to the mapping technique that has been used to produce the climatology. So due to that, you can see that you have very different estimation of the volume of oxygen minimum zone. If you take, for instance, the world ocean climatology estimation, or if you take some different mapping technique, and this is the table that show you the different estimation of the oxygen minimum zone volume for different regions using different technique, and you can see that you can have some difference. So now this oxygen cycling in anoxic marine zone is enigmatic, and here I am taking the example of the Black Sea. In the Black Sea, so you do not have oxygen below more or less 120 meters. You have a huge hydrogen sulfide pool. And here in the Black Sea, you have two floats with bio-optical sensors that have been deployed. So you have oxygen sensor, but in addition to that, you have bio-optical sensor in order to investigate what's happened in the transition between the oxic and anoxic interface. What you can see on the left is the temperature profile, the oxygen profile, and also the hydrogen sulfide profile delivered from these Argo floats. And on the right, what you can see is also the profile taken at one station. So you see the oxygen, temperature, hydrogen sulfide, and in addition, you can see the backscattering coefficient that can also be delivered from Argo floats. And this backscattering coefficient is very important because it gives you an estimation of the importance of particles in the region between oxic and anoxic regions. And we know that in this type of region, you can have a lot of particles that can be due to the shuttling of manganese oxide sinking, etc. So this particle can allow you to investigate the process that occurred there. So the question in the Black Sea was to know which process oxidized the hydrogen sulfide going out of the anoxic layer. Is it the physics or is it the biogeochemistry? And using this type of observation, the authors were more in favor of biogeochemical processes involving bacteria and involving the sinking of particulate manganese. So now for the prediction for the modeling of low oxygen zone. So modeling low oxygen zone is also challenging. So here you have the prediction for the end of the 21st century of the oxygen content of the ocean. You can see that the different models agree that the oxygen will decrease. The different color represent the different scenario. And you can see that in the different scenario, you have a decrease in the oxygen concentration going from 1.8% to 3.8% if you speak about the scenario 2.6, or if you go to the scenario 8.5. So the model agree on the trend of the global oxygen inventory. But if you look at the details, and if you look at the prediction of the volume of oxygen minimum zone by the different model, you can see that the model disagree. And here the picture show you the relative change of the volume of the Pacific oxygen minimum zone, relative change if you compare the end of the 21st century to the end of the 20th century. And you can see this relative change according to the oxygen threshold that you use to define the volume of oxygen minimum zone. And you can see that if you are below 100 micromole per liter of oxygen concentration, you have a big divergence of the model prediction as concerned the fate of the oxygen minimum zone volume. So what is also important is that if you want to address the dynamics of oxygen minimum zone, several studies have shown that the mesoscale processes are important. This is not exactly clear how you quantify that, but what has been shown is that if we speak about the Eastern Tropical North Pacific, you have some eddies that are able to ventilate the low oxygen zone by injecting rich oxygen waters in the oxygen minimum zone. So here in this region, it appears that the mesoscale process will contribute to oxygenize the oxygen minimum zone. Other studies have shown that in the Atlantic Ocean, these mesoscale eddies are able to trap organic material that will produce sinking material that will consume a high rate of oxygen, and that will produce low oxygen concentration that will be isolated from the rest of the region. And you can see here by this paper by Schut et al. In 2016, the position of these eddies with very low oxygen concentration in their site. This happened in cyclonic and also in anticyclonic eddies, as you can see on the picture on the bottom. So if we speak about the coastal ocean and the regional sea, the prediction is more on the shorter term, usually. So we are more in a spirit of forecasting the oxygen of the deoxygenation events in relation, for instance, to end user or to biodiversity, etc. And so here I am showing you the forecasting system of the Black Sea, because I am involved in this forecasting system, so I know it very well. So basically what we have is that we are involved for the prediction of the biogeochemistry. We are in a group with CMCC and University of Sofia for the prediction of the physics, and for the wave we are with the University of Hamburg, HZG. And so the model that we have solved the biogeochemistry from the surface to the bottom, so including the representation of anoxic process, and we also have a representation of the sediments. So in the frame of Siemens, what is very important is to have very accurate prediction. So on the right, you can see the validation of the model as concerned the oxygen dynamics. So the model and the data are shown here with a typical seasonal cycle, and also as concerned the generation of hypoxic records. All this quality assessment is available online on the Copernicus website, and then we try to link now with indicators of the Marine Strategy Framework Directive, because among these indicators, you have indicators that are related to the oxygen content of the water. So this is something for which they need to have a very accurate information. Another thing that is important and that we are delivering is the oxygen penetration depth in the Black Sea. So this picture shows you the estimation from observation and from Argo float of the oxygen penetration depths in the Black Sea. And we have seen that during the past 60 years, the vertical extent of the oxygen layer in the Black Sea has narrowed from 130 meters to 80 meters. There are several reasons for that, on which we can come back afterwards. So this is a prediction, this type of information. You can find it in the ocean state report produced by Copernicus. So in this report, you can have some estimation of the oxygen content of the water. You have a section on oxygen, and the information is also available online as ocean monitoring indicators. So losing, you have what is the impact now on marine life or deoxygenation. So we know that respiring for marine organisms it can be challenging. So marine organism in 1 liter of water, you have more or less at saturation 35 less oxygen that's in 1 liter of air. And if we speak about low oxygen region, you have oxygen content that is more several hundred lower than the oxygen content in 1 liter of air, if we speak about water that are 5% saturated. So this oxygen loss can alter a lot of processes that are listed here. Okay. So Okay, so this will control the taxonomic composition, so the oxygen can impact the different taxa differently. The crustacea and the fish will be the most impacted by the low oxygen condition. And then the challenge is now, if we move to prediction, how to predict the impact of deoxygenation from the lab to the ocean. And this paper here, published by Dutch in 2015, show how we can use a metabolic index of oxygen stress that is estimated by the ratio of oxygen supply to the organism divided by the oxygen demand by the organism. And this ratio can be estimated based on physiological parameters that can be estimated in the lab for the species that you consider. And it can also be estimated by the oxygen pressure that you have in the field. And this picture shows you the representation of the change of this metabolic index between the end of the 21st century compared to the end of the 20th century. And what we can see in this picture is that there will be a lot of regions where the metabolic index will decrease at the end of the 21st century. This loss of the metabolic index is due for one source to the decrease of oxygen, and for the remaining is mainly due to the increase of temperature. So this habitat loss has also been evidenced by Stramma et al. They have tagged blue marlins, and then with this tagging, they were able to record the migration of this blue marlin in the ocean. And on the picture on the right, what you can see is the level of dissolved oxygen. In red, you can see the region where you have very low oxygen concentration. And in blue, you can see the migration of the blue marlins. And what you can see is that the fact that you have low oxygen condition will reduce the vertical migration of the blue marlin and will reduce its habitats. So it has been estimated that you have more or less 15% habitat loss between 1916, and 2010. It's not 210, but 2010. Okay, and the last example that I will take is this example that also relates individual effect to population if impact. This is always very tricky to go to individual effect that you measure in the lab to the impact at the population level. This paper by Kenneth Rose has tried to make this difficult connection, and how they did is that they use a succession of modeling approach. You have different modeling approach. You have first you have exposure effect submodels that are shown here on the right. In this type of model, what you can see is the influence of oxygen value on some physiological process like growth, like reproduction, mortality, etc. Using this exposure effect submodel, they also have individual-based model that will follow individuals through the different development stages, so going from larva to juvenile to adults. And these individuals will use as oxygen estimation the estimation provided by a coupled hydrodynamic and biogeochemical model of the Gulf of Mexico. So this estimation has been done for the Gulf of Mexico. And you can see here the results of the oxygen estimation that have been used to feed the individual-based model. So based on that, they were able to make some trade-offs or recommendations for mitigating the food and hypoxia. So what you can see here is the number of individuals according to the time. In green, this is the number of individuals that you have if you have no hypoxia at all. This is what you have. In blue, this is what you will have if you keep the same level of nutrient and if you have hypoxia in the system, so you have a decrease. And in red, what you can see is the situation if you decrease the nutrients discharged by 25% and if you keep hypoxia. You have this decrease because, of course, if you have hypoxia, if you have high discharge of nutrient, you will have more food, and more food will sustain the development of more croaker organisms. So this means that you need to find a good balance between reduction of nutrient discharge in order to decrease hypoxia and keeping a certain level of food for the living organism there. So this type of model is trying to address this balance, these trade-offs between hypoxia and food. So to finalize, I would like to synthesize by these two concluding slides. So the global ocean climatology that have been published recently by Garcia, by Schmidtko, there are also climatology. Yes, there is also the climatology produced by GLODAPT recently. They do not yet incorporate the Argo oxygen data, but we can be optimistic that the recommendation for the in-air calibration will have the potential to deliver data of sufficient quality for assessing oxygen trend and for incorporating this Argo data in the climatology. I guess that a global coordinated assessment of deoxygenation in the coastal and regional sea is less advanced compared to the global ocean, and international effort would be needed in order to first promote the inclusion of regional data in international database in order to allow the mapping of oxygen and the production of climatology for the global coastal zone and also for the eastern boundary upwelling system. A SOCAT-like product for oxygen will also improve our ability to estimate the oxygenation in the global and coastal ocean. We have seen that we have problem for the oxygen minimum zone accuracy of observation, and there is some intercalibration exercise that have been started in the frame of CARINA, but this type of exercise could also be enlarged. So high quality data is needed for very low oxygen region. We have seen that there are very specifics, and this is needed if we want to help to parameterize biogeochemical models, because these biogeochemical models need to have very precise information on the threshold between the different biogeochemical process. This is needed for representing the dynamic of oxygen minimum zone. And this is also needed in order if we want to estimate the cycling of essential elements like carbon, nitrogen, phosphorus, and iron. So the prediction of the effects of deoxygenation at the spatial and temporal scale relevant for the ecosystem services are needed. So far, our models are usually at the kilometer scale, but we would need to go at the meter scale if we want to connect with the habitats. And also an estimation of the error prediction would be really needed, for instance, using ensemble of approach. There are some models that are starting like that. And finally, there are very nice review by Rose et al. On regional models' ability to represent the oxygen dynamics from weekly from daily to weekly time scale. So this shows that the model have some abilities, but this also shows that the performances of this type of model are usually hampered by the quality of the boundary condition. And boundary condition, I mean essentially the river condition and also the atmospheric condition, which is also the case for the global ocean. So to finish, I would like to show the ongoing activities that we have had during GO2NE. So we have a technical brief that is on press now, very soon published. We have review papers. The one has been published recently in Science in January. You can see here, so decline in oxygen in the global and coastal ocean. There are several other reviews that are in preparation. We are also organizing the GO2NE summer school examen in China in September 2019. It will be for PhD students. We have also activities in order to align with other networks to raise awareness. And we are also involved in the key conference on ocean deoxygenation that will be organized in September, and to where you are mostly welcome. So that's finished. I will finish with the picture of the group. So thank you to all of you for your attention.
Thank you very much, Marilaure. It was great. And I open the floor to questions. I hope we will receive a few. You can just type in your questions in the little box there you have in your webinar. I think this should be possible for everybody. In the meanwhile, I would like to ask you a few questions, maybe. Really great talk, a lot of new findings as well for me, and very nice graphics. And it's very interesting to see all those different influences for deoxygenation in the ocean. And very important is most probably as well, what is the natural variability within a year, within a decade? So what do you think? How much does this make? How important is this natural variability in a year, in a decade, compared to the loss by climate change and eutrophication, maybe?
Yeah.
Can you hear me? No.
Yeah. I can. Can you hear me?
Yes.
Yeah, okay. So I mentioned maybe briefly this paper that it is not the only paper addressing that very difficult question, but the paper by Dutheil et al. That is now on discussion on biogeoscience, so a peer-reviewed journal. And so this paper estimates the impact of the Pacific decadal oscillation that will affect the trade winds flowing over the equator and impacting the general circulation there. And so this paper addressed the impact of this Pacific decadal oscillation on the oxygen content of the equatorial tropical Pacific. And what they show is that the shifting from a negative to a positive phase of this Pacific decadal oscillation can lead to very important reduction of oxygen content in the oxygen minimum zone of the tropical ocean. And this has also to be taken into account. This has also to be understood. So this is significant. Of course, this is very difficult to address the impact of natural variability because, for instance, as concerned the Pacific decadal oscillation, you need to make simulation of at least 50 years. So it means that you really need to have very long time simulation in order to extract from the natural variability signal the anthropogenic signal. And so this put a strong challenge above our heads because these long-time simulations are very time-consuming. But this seems to be not negligible, and this is taken into account in a lot of paper. This is discussed in a lot of paper, but this is not easy.
Yeah, there's also this latest paper by Ostlis et al., which I think was very much discussed in the community as well, and I think also brings a totally new light onto this whole new field. There's one question here by one of the participants, and I might just read it out, that you, in one of your slides, you mentioned that deoxygenation is very slow with minus 0.06 micromole per kilogram at 300 meter steps, which is about minus 0.03% considering DO is around 200 micromoles per kilogram. But in the IPCC slide, you mentioned that the deoxygenation is 1.8 to 3.5%. So I think there's a missing link with the timescales because, as you said, what you were mentioning was per year, and this what is mentioned in the IPCC when we had like deoxygenation is increasing or oxygen is decreasing about 1.8 to 3.5%. This is not only per year. Huh?
No,
Am I correct?
In fact, this decrease of a few, of a few percent per year is for the prediction at the end of the 21st century. So this is for the So this is the percentage of change for the end of the 21st century. So it's about 100 years of simulation, and the decrease that has been mentioned here. I guess this is the decrease per year. This is the decrease per year that we have at 300 meters. So here, this is a decrease per year. Yes. Okay, and the other one, it's a total decrease of the oxygen inventory.
Yes.
And here, this is a decrease in concentration. This is a trend in concentration here, and the other, this is a decrease of the oxygen inventory.
Yeah, there's another question about the impact of salinity or the role of salinity in terms of deoxygenation. Can you give any hint on that with the freshwater influence or whatever, how the changing salinity is also influencing deoxygenation? Is there any?
So salinity is okay. So in the Black Sea, this is really the salinity stratification that will create the innoxic water. So salinity can play, of course, a role also in driving the deoxygenation. So now, as concerned the possible trend that we can have in the salinity, I guess that this is a little bit addressed in the Schmidtko paper. If they mention, I guess that they mentioned if the freshening of the Arctic, how it will impact the deoxygenation, but I do not have exactly in mind what was the signal. So I am sorry here. I do not have that in mind, and I'm not sure. So I prefer not to say something on that.
Another question, and also congratulations to your talks from one of our listeners, from Roberto Sabia, asking what would be the benefit of, or to which extent you believe satellite remote sensing could be beneficial to the overall deoxygenation community, for example, estimating surface biogeochemical values. Do you see how remote sensing data could contribute to improving the models, to improving the existing data sets?
Yeah, so okay, so I would say that the satellite observation is really an important source for validating this model. The model that we are using for predicting the oxygenation are really validated using a satellite observation. So it means that we compare the prediction with satellite observation. So it can be the sea surface elevation, so it can be the sea surface temperature, it can be the chlorophyll estimation, which is also very important to see if the model is able to simulate the right productivity, especially for the coastal region, because this is really the bloom that will create the deoxygenation event on the bottom. So this is very important, of course. This is also important because a lot of models, and this is maybe more the case in the regional and coastal ocean, assimilate a lot of data. This is also the case by the global ocean, by the way. So, and these satellite data are simulating in the models in order to improve the prediction. So I guess that like that, the satellite, of course, can help in improving the prediction of the model, in improving the validation of the model, and also improving maybe the detection. Yes, this is also something that could be important, the detection of mesoscale activities. And I know that in some papers, so when I spoke about the mesoscale, here, I know that they also use satellite observation in order to be able to detect, to try to find a procedure to detect the eddies where you can have this low oxygen condition. So they try to make some connection between these eddies with low oxygen condition and their signature as sea surface temperature and sea surface elevation. This is not straightforward, but they are trying to do that. So for the mesoscale investigation.
Yeah, another question from Pierre-Yves Détran. What is the recommendation of the GO2NE network for Argo? Are floats, all floats with oxygen sensors, regular array, only in the OMZs? What would you recommend for improving the oxygen coverage via the Argo floats?
Yeah, so I can say that there are several points to this question. As concerned the quality, the type of sensor that we can use, so we really have to have sensors that are able, if we are targeting anoxic marine zone, that are able to detect this very low oxygen concentration. So that's very important. So then there are a lot of other sensors that can be helpful for oxygen minimum zone, as we have seen in the Black Sea with nitrate, with chlorophyll, etc. But there, I guess that some quality estimation has to be a little bit done as concerned the accuracy of this nitrate concentration and the chlorophyll concentration in this type of region. But I know that it is ongoing. I guess that we know that they are challenging. We know the deficiency of the current sensor. So I guess that everything is in the literature. We also know that there are gradients. So we need to have sensor that can react rapidly enough in order to detect the gradient, because the gradient are also very important in the oxygen minimum zone. So this concern the type of sensor that you can use as concerned the accuracy, the precision, the lifetime, the gradients, the response time, etc. But then what is also important is to know where to deploy this sensor. And where to deploy the sensor can be done in collaboration with modelers using observation system simulation experiment, for instance. So it means that what you did is that you make a simulation, in your model, you consider that you deploy a float at a certain part and you just look how this float will be propagated. And you try to optimize the deployment area in order to try that this float stay in the oxygen minimum zone. This is difficult, but I know that there are already studies that are doing that in order to optimize the deployment of the float using models. So this is also something that I have found.
Yes. Another very interesting question, I think, from David Barnes is, in the beginning you said that warming-induced solubility changes only account for 15% of the apparent decrease in oxygen. So what is the calculation behind, and how is this determined?
How is it determined? How, when? I don't remember exactly how it was determined, this percentage of change.
I think this was also something from Andreas, who explained it via those IPCC models as well, diverge a little bit.
No, I think, yeah, it's also maybe it's also done in the Schmidtko paper. So you can estimate that, I guess, from models, but also from observation. And I don't have in mind directly how it is exactly done in the observation, how they come to this 15% number.
Okay, so definitely something we have to follow up again.
But it should be very straightforward to do that. But
yes,
yeah.
Yes. Another question from Laila Kito. Do you think that the uncertainty of oxygen content and thresholds, natural variability in oxygen content, and major oxygen minimum zones is one of the major challenges to understand nitrogen fixation in those areas? So,
I guess that this rising of the oxygen minimum zone would have an impact of nitrogen fixation if we consider that this oxygen minimum zone are site of denitrification. Provided that the oxygen content is really low, almost zero, you will have denitrification. If you have denitrification, you will unbalance the nitrogen to phosphorus ratio, so you will have more phosphorus than nitrogen. And we know that this type of condition will be advantageous for nitrogen fixers, providing they have enough iron. And this iron, it's possible that this iron comes from the emission of iron, the extensive emission of iron from the sediment that are covered by low oxygen regions. So this is a source of possible iron. But I guess that there are a lot of uncertainty on that, on how nitrogen fixation can react to this unbalance of nitrogen and phosphorus and possible enhancement of iron. There are a lot of things that need to be further here in order to understand how it works and if it's able to compensate for denitrification.
Yeah, and especially in coastal areas, I think where you also have a lot of eutrophication, and so actually a lot of algae grow very fast who don't need to do nitrogen fixation, outcompeting those then as well, because there's not this imbalance of reduced nitrogen, for example, in the Baltic Sea. I think that's also something.
Yeah, in the Baltic Sea, they have this problem that they change the nitrogen discharge and not the phosphorus discharge, and so they imbalance the nitrogen-phosphorus ratio, and this favors the development of harmful algal bloom. So this means that we have to be very careful when we make mitigation strategies. It is described in a Daniel Conley paper. And so that's this balance between nitrogen and phosphorus that can be imbalanced due to deoxygenation is a very tricky point.
Yes. Another very important question, and first it was to thank you for Matthias Rothe for this interesting talk to you. How the increase of oxygen minimum zones will also affect the production dynamics of methane and methane production, and what do we expect there for the future?
I was not really able to find very strong information on that. What I have found is that in this oxygen minimum zone, when you have production of methane, so it means that you have used the nitrate, you have used the manganese oxide, iron oxide, and the sulfate, and though you comes to CO2, this is really the last oxygen that you can have. In this region, when you have the production of methanes, usually it is oxidized in the water column and it does not. This is the succession of process that you have around an oxygen minimum zone. So, so you have first denitrification, and then if you do not have oxygen, you have the other process that can happen. So methane production is really the last one. So when it is produced, the methane can be released, but it will be probably oxidized in the water column before escaping to the atmosphere. So I have not found a very concluding remark, and it was even the reverse, that you can have an emission of methane due oxygen minimum zone. So because usually the methanes will be oxidized most of the time in the water column.
Yes.
For the nitrous oxide, this is maybe not so straightforward. So it's it should be. We know that you can have production of nitrous oxide, but what we still don't know if it's this nitrous oxide will be converted to denitrogen, or if it will stay nitrous oxide and then will escape to the atmosphere. So this is something that is more maybe more relevant, the nitrous oxide production and escaping to the atmosphere. But for that, we really need to have information of the threshold for knowing when this nitrous oxide will be converted exactly to denitrogen.
Yeah, maybe just one last question before we have to finish, because the time is flying and the hour is almost over. So what do you expect, a question from Valeria Ibello, how do you think that the increase of oxygen minimum zones would the microbial community and overall efficiency of the carbon pump, and so as well the carbon export to downstream, and how, if you have any examples for that, for example, for the Black Sea, she's suggesting that there would be a decline of carbon export, and so what do you think?
To the deep sea,
did you? Yes.
So it means so I don't think that we have also a very clear answer on that. What I can say is that if you are in the coastal region, it's here. If you are in the coastal region, when you have this oxygen minimum zone forming on the bottom, you will promote the release of phosphorus and iron that will stimulate the primary production. And so you will have an increase of primary production, and you can have also an increase of the carbon barrier in this type of coastal area. For the deep sea, for the open ocean, I guess that it is this is very difficult to know, and then I'm not sure. I don't think that there is an agreement on how this oxygen minimum zone can impact the amount of photosynthesis. So this is difficult because it will also depend on how this oxygen minimum zone will change the flow of nutrients, of nitrate and of phosphorus from the to the surface layer. And we see that this oxygen minimum zone can change this flow of phosphorus and nitrogen by denitrification, by the release of phosphorus. So we see that it has the potential to change the amount of primary production, but it's not clear what will gain, if it's the release of phosphorus or if it's the consumption of nitrogen. So this is really a difficult question.
Yes. Thank you very much, Marilaure. It was
Thank you.
A great webinar, I think, and I hope everybody who joined us also enjoyed it. And so we will. It was recorded and it will go online so that you can share it with your colleagues and also consult it later. Again, feel free to contact Marilaure, I think, if you have any further questions. And yes, thank you very much, Marilaure.
Thank you. Thank you to everybody for listening. Thank you.